Okay, so I'm going to talk about section 4.2. So this is a week 2 module. Okay, so we're going to start with the natural exponential functions. Okay, so first I'm going to talk about the number e, so where number e is coming from, and then we'll talk about natural exponential function, and then some applications called continuously compounded interest. Okay, so any number that can be used as a base for an exponential function. So we can use any positive number for a base. So for instance, we can use this number as a base, 2 to the x, or we can use 10 to the x, and etc. So, but over here we're gonna talk about a special base called e, and the reason is because this e, this number, basically it's a number, e comes from the Euler, so it's an Euler number, and it has a very important applications in calculus. So okay, so now we're going to talk about number e, and the number e, there is this function. So if I write this as a function, if I write this guy as a function of n, so f of n equals this guy, then we just want to know, what happens to the y values of this function when n becomes so large. So here is some experiments. I'm going to show you some experiment in this table here. So let's say n is 1. Okay, if you plug 1 into this expression here, you'll get 1 plus 1 over 1 to the power 1, which will give you 2. So that's this number. If you plug 5, so you're going to get 1 plus 1 over 5 to the 5, and then you're going to get that number. So if you keep on plugging 10, 100, 1000, 10,000, so you see slowly the n values are getting so large, right? And when n values are getting so large, then the values of this function seems to be localizing close to such a number. Okay, so then we're saying that as n is going to infinity, right? Then this function f of n, which is defined as 1 plus 1 over n to the n, is approaching to 2.71 and so on, right? So then we're going to call this number e, which is in close to 2.71820. So this is also a key in your calculator. So if you look at your calculator, you'll see this letter e, and you press on this. So if you click on this number, you will see that you're getting such a thing. I'm not sure if calculator will show you all these digits, probably not all of them, but some of them at least. But most of the time we say, okay, we're just going to round e to the 2 as 2.71. Okay, and we can use this number also for the basis of an exponential function. So for instance, I can define a function and write it like this, e to the x. So we say this is an exponential function with the base e, or a natural exponential function, some people call. Okay, so that's where e is coming from, and you will see this, in calculus and in other math courses all the time. Okay. Now, the number e is base for natural exponential function, we said. So why such a strange base for an exponential function? So it might seem at first that a base such as 10 is easier to work with, but now we will see that in certain applications, the number e is the best possible base. Okay, so we'll look at that. For instance, in compound interest, and that's like what we will talk about at the end. Okay, so now let's define precisely what the natural exponential function is. The natural exponential function is an exponential function, is a type or a special type of exponential function with the base e defined as f of x equals e to the x, where e is called the base of the function. All right, so this is how the graph of it will look like. I mean, the graph is nothing different than other exponential functions, but since e, the number e is between 2 and 3, so then it makes sense that the graph of this function will be between the graph of 2 to the x and 3 to the x. So because you have this relation, when 2 is less than e and e is less than 3, then you will also have 2 to the x less than e to the x and e to the x less than 3 to the x. So the graph of this function is going to be between the graph of 2 to the x and 3 to the x, maybe more closer to the 3 to the x, because this number is more close to 3 than 2. Okay. So now let's do some calculation with the e. So for instance, if I'm going to calculate e to the 3, so then I will just press the e to the x function, right? And then just put the 3 as a power of e, and then we'll have this approximated number. Okay. So we're not going to do those things by hand, but we will do a lot of algebra with the e as well. Okay, so for instance, for b, you're just gonna put this function as it is, or put this expression as it is in your calculator and find an approximated value. So, and then same thing for c. So this will be e to the, so you press the e and then the power button, and then write 4.8, and then you'll have the approximated value of that as this number. Okay. Now here is another application problem that E is involved. Okay, so an infectious disease begins to spread in a small city of population 10,000. After T days, the number of people who have succumbed to the virus is modeled by this function. So how many people infected are there initially? Initially means the time 0, right? So whenever the time is 0, then that's always the initial population. So all we will do is plug the 0 in T and then evaluate it, right? So I'll show you that on the next page. And then for part B, we will find the number of people who are infected after 1 day. So after 1 day means T equals 1. So I'm going to evaluate this function at T equal to 1. And then I'm going to evaluate this function at T equal 2 and T equal to 5. So 3 different values, and we'll find 3 different populations at those days. Okay, so here are the answers. So 10,000 divided by 5 plus 1245 e to the 0, because I plug 0 for t. So e to the 0 is always 1, because 0 power of any number is 1. And then you'll get this number on the bottom because you add it to the 5. So 10,000 divided by this number is 8. So initially there were 8 people who were infected with this disease. And then now after 1 day, let's look at the number. So after 1 day, you're just going to do this, right? You're going to do V1 equal 10,000 divided by 5 plus 1245, and e to the what was that number? Negative 0.97 times 1. So we will do negative 0.97. Okay, so if you put this in your calculator, then you will get 21. And then similarly, you'll put a 2, you'll get 54, and then you get, so you see these numbers are exponentially growing. Okay, so okay, and here is the graph of this function, and you will see that that's an exponential graph. Okay. So, and you can see that the number of people infected rises slowly first, but then rises quickly between day 3 and day 8, and then levels off when about 2,000 people are infected. Okay, so when this gets bigger, so it's probably just going to level off at some point, right? Okay, now the application. So let me tell you about this applications of E. So we talk about compounded interest formula, and now let's see where E is going to fit in here. Well, let's take this formula, and you're familiar with this now because we talked about in the previous section, right? This is a compounded interest formula, where P is the initial value, R is the rate, N is the number of times, and T is T. So we're just going to tweak this a little bit. So we're going to let M equals N over R. Okay. R over N is already there, but I'm just going to call M equal N over R. Therefore, I can now change this, okay, because see this one, N over R times N over R times T. So R will cancel, you still have N times T. So this is actually N times T, but I write I write n times t as n over r times r over t. And you'll see why we do that now in a little bit. So, and I'm calling n over r to be m. So this guy is going to be m now, okay? And then this will be 1 over m because it's a reciprocal of that. So p times 1 plus 1 over m to the m to the r over t. Now we know that when m becomes large, then this quantity, okay, this quantity from the definition of e, this becomes e, right? So when m goes to infinity, then 1 plus 1 over m to the n, that's just the definition of e. This will go to e, right? So then this whole thing is just going to be e. So then you get this formula. You get a equal to p times e to the rt, which is a formula for continuously compounded interest. Okay, so this expression is going to give us the amount when the interest is compounded at every instant. Okay, now let's summarize the formula. So continuously compounded interest is calculated by this formula, where again, P is going to represent the principal, the initial amount, R is the interest rate per year, and T is the number of years, and A will be the amount after T years, so the total amount. So maybe I should say this total. This is a total amount. Okay, now let's look at an example. Okay, so find the amount after 3 years if $1,000 is invested at the interest rate 12% per year, compounded interest rate. So when you see this, you're not going to use compounded interest formula. You're going to use continuously compounded interest formula, which is A equal to P times E to the R times T. And the P here is 1,000, so that's this. And R is 12%, so R is 12%, but you can write it as 12 divided by 100, which is going to be 0.12. And T is 3 years. So then I'm just plugging everything in this formula right here. Okay, so P is 1,000, E to the 0.12 times 3, and 0.12 times 3 is 0.36, and then I'm just going to put this in a calculator. So use your calculator here. When you do that, you will get this amount. So remember, when we were doing example for compounded interest, we said that putting daily, brings you more money. But now we put the continuous on top of that. So when you do it because you do it at every instant, right? So when you do it compounded continuously, then you will get more amount after a certain number of years. Okay, so that's basically an introduction to this topic. So okay, so we'll continue with 4.3.